All right, so we're going to do the full USHAG problem today, and then on Wednesday, we're going to do the deltas. So we're going to have reactants and products, calculate the equilibrium constant, all of those things on a 2 or 3 level system. It's a 3-level system. And so we're going to go, this is the full statistical thermodynamics analysis. So just taking statistics and applying it to a 3-level system, we're able to calculate all the thermodynamic properties. Now, last time we spent a fair bit of time talking about energy, internal energy, and the heat capacity. But today we're going to focus on energy and go all the way through the Gibbs energy. And we won't do the equilibrium constant because for that you need reactants and products. Okay, but we're just going to do the reactants today. I'm going to go slowly so you guys can fill in the gaps in the notes and ask questions. Okay. So again, we have that decision point. If you're dealing with moles of materials and so on, and just put this in here review to make sure it's still in this set of notes. This is not what you would use for a 3-level system. Okay, this is what you would use if it said, you got 10 moles of gas at room temperature. What's the internal energy? And so you've got to take into account the translation, the rotation, and the vibrational energies. Most of the time, the vibrational energy is 0 because we don't have active vibrations. Okay, and so the total is the sum of all of those. This little last line is not in your notes, but I wanted to make sure I added it. I was going through. I was like, I need to tell them that the total is just the sum of the energies. That wasn't the case for the partition function. For the partition function, the total is the product of all of them. So you got to know the difference. It's like when you're doing the partition function, it's Q rho times Q vi times Q trans. That's the product of all the Q's. But for energies, things like enthalpies, energies, all of those, entropies, it's just adding them all. Okay. So this is what we would use for like a 3-level system. We would sum up the Boltzmann factors for all of those, multiply them each by the energy, divide by the partition function. And essentially what we're doing is we're taking the probability of being in each state times the energy we get from that state, adding it up. So that's the average. It's this normalized probability that comes from the Boltzmann distribution and the partition function. It gives us our normalized probabilities. And then it's just obvious. I have 50% probability of being in this level, then whatever the energy is of that, I get 50% of the whole. So let's go ahead and calculate the internal energy. And if we have that, then we can calculate all of these others. You can see it build. So internal energy and partition function are used for entropy. The internal energy goes into the enthalpy when you add in the temperature piece. Internal energy goes into Helmholtz energy when you take this entropy and temperature piece multiplied by each other. And then the same for the Gibbs energy. It's enthalpy minus the temperature times the entropy. And so let's calculate this. This is a typical kind of problem you would see in a 3-level system. So calculate the partition function at room temperature. And so we would just calculate those Boltzmann things. Now for the KT, when we're dealing with wave numbers, 0.695 wave numbers per Kelvin times 298 gives us roughly 200 wave numbers. So we can use that in this problem to save us some time. So this one here, this is going to be, of course, e to the minus 0. So that's going to be 1. But then this one is going to be e to the minus 200 wave numbers over 200 wave numbers. So e to the minus 1. And that's going to be the 0.38. And this top one is going to be e to the minus 2, because it's going to be e to the minus 400 over 200. The 200 being the room temperature piece. So everybody see how that, I kind of made it easy for you guys. But here in the denominator of the exponent, you have KT. And in this case, KT is roughly 200 wave numbers. So that's what we have for our Boltzmann factors. add those up, you get 1.53. And so that's the partition function for this. So it's, again, this is telling us that we have, on average 1.5 energy levels populated. Okay, so we have most of the molecules down here in the ground state, and maybe something like this. Okay, 40, like maybe 40%, and not even 40%, maybe 25% and 10%. Okay. But let's calculate those percentages. So if we take those same Boltzmann factors and we divide each by this partition function, we get the probabilities. So in this case, it's 0.14 divided by 1.53. And so we get 10%. And so then the next one is 0.38, or a little bit more than twice that, so 25%, and then 66%. It ought to add to 100. It looks like 6 and 5 is 11. Okay, 6, 7, 8, 9, 10. So it looks like we've got 101%. Okay, it's a little rounding error in there somewhere, but we're close to 100. What does that mean over here? Well, let's, if we put 66 dots here, we'd have 25 dots here, we'd have 10 dots there. Okay, so that's what the Boltzmann distribution looks like in a system without degeneracy. So if you were to kind of look at it on the side, you see this is an exponential decay. So that's something I think mentally you need to think about, that as you look at the excited state molecules, you have this e to the x function. It's kind of like a bar chart, right? It's really big at the bottom, smaller and smaller, drops off as an exponential decay. What is the half-life? If we're trying to thinking about kinetics, what is the half-life? Well, it's kT. Okay, if kT is bigger, it doesn't drop off as fast. If kT is really small, it drops off really fast. So at cold temperatures, it would look like this. It would drop off really fast, and you'd have really low probability of being excited. And at high temperatures, it would drop off really slowly, and you would have equipartition. You'd have equal molecules in each of the three states. So does everybody understand what I'm plotting? This sort of the sideways we're looking at it. We're looking at an exponential decay in the population of those energy levels. Okay, now let's take their probability and multiply by the energies. So we have 10% chance of having 400 wave numbers. So there's the rounding. I kept all of my digits, so it's really 38. And then it's a 25% chance of being 200 wave numbers, and 66% chance of having 0 wave numbers. So we don't get any energy from that ground state. So even though that's the most popular state, it doesn't give us any energy to our system. And so when we talk about the energy of a system, we're talking about the average energy. If we were to sample that system over and over again and average all of the energies we would get that average energy. If we pull a bunch, let's say we have a bunch of these molecules in a bag, we reach in and say, what's your energy? Okay, 66% of the time they'd say 0. We're like, I don't care about you. Then you pull one out and it says 200. Okay, write that down. 400. Okay, write that down. And then we average up all the numbers that we got, we would get this, 87.9 wave numbers. Now that's interesting because if we have these molecules in a bag and we keep pulling them out, we would never get one with 87.9. So that's kind of weird to break your brain, right? It's the average energy of the system, and not one particle in the system has that energy. It's the same as kind of having the average number of kids in the United States be like 1.7. Nobody has 1.7 kids. Okay, so this is quantum effects. It's the whole numbers, right? You're in the first excited state, the second excited state, the ground state. But you have these quantum effects where no matter what you pull out of there, it doesn't have the average energy. But if you take the overall average of these quantized states, you get a number that's not represented by any one level. So this, it's less than 100, so it's probably right about there. So that's the average energy. 87.9. Y'all are just totally cool with that. I mean, it's hard to, I don't know what I'm saying. It's bizarre when you get down to it. You start analyzing small systems like this, you get down to the quantum levels and you're like, wait a second, I get discrete levels. I pull a molecule out and it's 400 wave numbers. I pull another one out and it has 0, these quantum jumps. And yet you average over a whole chunk and you get this 87.9. Okay, so now let's look at the entropy. So entropy, again, the statistical entropy was derived by Boltzmann. This is his tombstone. So how cool is that? On his tombstone, he has his equation for entropy right here. I mean, that's a goal for a scientist, right? To be like, have an equation and in the Boltzmann constant, his constants right here. It's that proportionality that turns the statistical weighting factors for these energy levels, which we kind of determined just now, into the entropy, using his constant as the conversion factor. And so here's his younger days, and that's his signature. I don't know. I like Boltzmann. He's who a lot of people say Max Planck or even Schrodinger and those guys were the fathers of quantum mechanics. And yes, they developed the math, but he's the first one that did a quantized math equation. So he was determining the distribution of velocities in a gas. And he said, for the simplicity of math, I'm going to pretend they have discrete velocities. So multiples of a small velocity. So basically he did it like in Excel, but he did it by hand. He didn't have Excel. But he said, all right, let's just calculate increments of velocity, which is discrete velocities. And I'm going to solve this problem, row at a time, like we do in Excel. And he said, but I don't mean to say that nature is discrete, but it is. Right? And so his math using discrete levels, the sum ended up being the Boltzmann distribution, and Planck used that to solve the black body radiation curve. And so Planck was really bothered by that because he was saying, I'm using discrete mathematics to solve this term for this black body radiation curve, and it seems to suggest nature is quantized, like little energy packets, solves this problem. So the entropy can be described in terms of the number of states that are available at a given temperature. We know this. These are the weighting factors that Boltzmann did purely by statistics. So W is weighting factor. For each of the different states. And so we've done sort of that by use the partition function. And the partition function, if we're looking at the partition function in a system of identical molecules, and here this is Avogadro's number. Then you would be dividing by Avogadro's number. Remember, the difference in logs is also a quotient. And so we could just simplify that and lump all of this into a constant, which we'll find later for I think it's the third law of thermodynamics, that this constant is set to 0 at absolute 0. And so essentially entropy is proportional, even though it's a log dependence, on the partition function. This partition function is taking the place of these weighting factors, using Boltzmann's distribution. And then this other part emerges too. It's the internal energy divided by the temperature. And so we know what this is. We just calculated it. We also used the partition function to calculate the internal energy, and we know the temperature. The only thing we have to really check is this R, because the units of our energy will determine what R we use. So that's the only trick in this problem. The times when I've had students email me panicked on a Saturday because their homework is due, it's because they're using the wrong units for R and energy. They don't match. And so they're not able to figure the problem out. So let's do this. Let's calculate the average entropy. So here's our internal energy, 87.9. And here's our equation for entropy. And I think I went into your notes and I blanked out this R value to emphasize, right? If you look up R in the book, you're going to see R is equal to 8.314, I think, joules per mole Kelvin. Okay. But remember when we looked at like KT and we were changing the Boltzmann's constant, which is K is equal to 1.38 times 10 to the minus 23 joules per Kelvin. If we wanted to make that, that's a 10, not a W. If we wanted to make that into joules per mole, if we multiplied that by Avogadro's number, 6.022 times 10 to the 23rd per mole, this becomes R. It becomes 8.31 joules per mole Kelvin. Yeah, so the ideal gas constant is Boltzmann's constant multiplied by Avogadro's number. Okay. And so that's where we get that. Now, if we were to take R and divide or K and divide it by Planck's constant, K over hc, this equals the 0.695 wave numbers Kelvin. So we have lots of versions of K. We could use K by itself. We could use R. And we could use K over hc. All of these three can go in that spot. So how do we know which one to use? We need to go over here to our energy level diagram and look at the units of energy that we have. So in the problem, you might have a problem where it says the energy levels are separated by whatever joules. And if it's joules, then you're going to use K. If it's joules per mole, you're going to use R. If it's wave numbers, you're going to use K over hc. And so this, what I've done here is this is energy, which would be in joules, but divided by hc, which that means it's in wave numbers. So anytime you see energy over hc, like E over hc, that's going to be wave numbers. So I think that's probably an illustration of one of the difficulties of thermodynamics is all of these equations, you had to know the units that you're going to use. So whenever I look at your work, I definitely want to see that you include all the units because that's going to save you all kinds of headaches. Yeah. If you're one that just wants to use the numbers and type them in your calculator, you're going to make silly mistakes and it's going to waste hours of your time. Okay, so these are the two pieces of that equation. The 89.9 divided by 298 is 0.295, and then this other piece is 0.294. So we have 0.589 wave numbers per Kelvin. So that's how much entropy we get with every degree of Kelvin. So another thing too is if you increase the temperature, entropy goes up. So you raise the temperature, you get more entropy. You get a half a unit of entropy in terms of wave numbers for every degree Kelvin that you add. So if this is at room temperature, we would multiply that by 298 to see how much entropy we're getting in terms of being at room temperature. Okay. So let's calculate the enthalpy. So here's our internal energy. We don't need the entropy for this one, but I just have it listed. Here's the equation for enthalpy, U plus RT. So once again, we got to pay attention to the R that we use. It's just in there sort of as a placeholder to show either K or R or K over HC. And so in this case, we're using K over HC. Instead of R. So 87.9 plus this piece gives us 295. So that's the enthalpy. That's the heat. We don't have a reaction, so we can't say heat of reaction. It's just the heat present in the molecule that can be pulled out by expansion work. Okay, let's go to the next one, the Helmholtz energy. Now I added this piece to your notes. Helmholtz, or delta A, when we have a reaction, that indicates spontaneity in constant volume systems. Now we use Gibbs energy in most of our classes at the university. Now, y'all have talked about Gibbs energy and organic and all of those different courses. And the reason being is most of our synthesis and experiments in the academic realm are done in glassware. Okay, glassware is a bit fragile and it can shatter and it can injure students. And so we always have open systems. So when we're refluxing and whatever, we have it open to the atmosphere, so it's at constant pressure. So Gibbs energy is at constant pressure, but the Helmholtz energy is at constant volume. That's what we use in chemical engineering. So if you're dealing with a reaction vessel, a stainless steel vessel with a pressure containment system, the pressure can go up and down, but the volume is fixed. How do you know if a reaction is going to be spontaneous in a reaction vessel? The Helmholtz energy. And so that's just one that we don't really teach much until you get to thermodynamics. So we're going to need the entropy for this one and the internal energy. And this is U minus TS. So the internal energy minus the temperature times the entropy. And so once again, that entropy piece is wave numbers per Kelvin, but we multiply by the temperature. And then we get the Helmholtz energy when we add in the internal energy. So don't be bothered that it's negative. Okay, you're looking at that, you're like, wait a second. We're going to be dealing with the reacting system on Wednesday, and you'll see that both of them are negative, and we take the difference, and we get, whether it's spontaneous or not, we get a positive or negative value for the delta A. Okay, so even though Helmholtz energy is tied to spontaneity, just like Gibbs energy is, we're not calculating deltas here. We're just calculating the Helmholtz energy of this system. Well, because we're not doing a delta at this place, in this situation, we're just the reactants. I don't know the significance of why it's a negative. Okay, I'm just not bothered by it. Okay. And so when we do the deltas, if it was negative, it'd be spontaneous. If it's positive, it'd be non-spontaneous, or in the reverse would be spontaneous. Now let's do the Gibbs energy. Okay. So same kind of problem, but now we need the entropy and the enthalpy. So we combine those two to make the Gibbs energy. So G is H minus TS. So we pull up, we go to a previous page, we find the enthalpy, 295 wave numbers, to subtract the temperature times the entropy, and we get the Gibbs energy, 120. Okay. And so, the internal energy in our system was plotted here, at 87.9. Okay. And so then the Gibbs energy is taking into account the entropy of the system too, and it's coming in at 120 wave numbers. Okay, so now let's look at these thermodynamic values. So these are all of the ones, and just again, a review of those equations when we're talking about wave numbers. We have energy is equal to Planck's constant times the frequency. The frequency is the speed of light over the wavelength, and 1 over the wavelength in centimeters is given this nu tilde. Okay, and so what we've calculated is all of our energies in wave numbers. So these are the numbers that we've been calculating here for this system, and essentially it's E over HC, right? Let's do it over here. E over HC is equal to that nu tilde. If we want to get back to energy in terms of joules per mole, then we just need to multiply our wave number values by HC. So that's Planck's constant and the speed of light. And if we want the per mole, we need Avogadro's number. And so what I've done is I've just put, again, Planck's constant, that's 6.626 times 10 to the minus 34 joules times seconds. C is 8.00 times 10 to the, and I'm going to say the 10 to the 10th, look at this, centimeters per second. Because that's got to cancel the wave numbers. And then Avogadro's number, 6.022 times 10 to the 23rd per mole. And so now you can see that the wave numbers cancels with the centimeters. This per second and the speed of light cancels with the second in Planck's constant. And then we're left with joules over moles. So that's what we get. Oh, 8. I did. Yeah, I was thinking 10 to the 8. That's why I wrote 8. Thank you so much. All right, 3. Okay. I got to give you a sticker for that one. If you find a mistake, I just really want to emphasize that I'd rather you not be silent, and leave a sticker on the screen. I mean, leave a mistake on the screen. So you put it on the front of your notebook if you will. All right. So good job. What's that?
Oh.
All right. So then I did this to all of these values. Yeah. So there's the entropy 7 joules per mole per Kelvin. The enthalpy 3,529. The Helmholtz energy negative 1047, and then the Gibbs energy 1431. Okay. So. We could convert all of our energy levels too and see what those are in joules per mole as well if we wanted to. What are your thoughts? Okay, sure. Keep writing. That's fine. Yeah, I had a lot of blanks on this page.
So for the energy, it was an average.
Mm-hmm.
For enthalpy, is that also average?
Yeah, these are averages for all of them because we use the quantized average energy to calculate all of them. So these would be the average enthalpy, average entropy for all the system. In fact, I don't know that, certainly the entropy doesn't make sense for a particle in a single state. Yeah, it's the whole system. So all of these figures of merit are single numbers to describe the whole system. Yeah. That's a good question or good observation. Yeah.
So how would we apply this to a real life?
Good question. How would this be applied to real life? The simplest example would be if you've got, one of the examples I can think of is like a molecule that's bound and a molecule that's dissociated, okay? Because that's a 2-level system, bound and dissociated molecules. And so you could calculate at a given temperature what percentage of the molecules are broken up and what percentage are bound. Like if you've got, chlorine inside this tube light and you got the bond energy for chlorine, and you wanted to know how many free atoms of chlorine are in there, you could calculate the temperature and the bond energy. That would be your 2-level system. At a given temperature, your excited state would be 2 free chlorine atoms, and in the ground state would be the bound chlorine. And then you could determine the entropy of the system, the enthalpy, and so on, and you could see how it changes with temperature. So that would be an easy quantized system that's a 2-level system. If you had a reacting system where maybe the chlorine could bond to something else and make a different molecule. So maybe we have fluorine and chlorine gas, and then you have a probability of them being dissociated and making ClF molecules. And those would have a different level. So you could see what's the equilibrium between these two gases in this chamber at a given temperature. And that might have important effects. I don't know that system does, but you could come up with and we haven't done the reacting system yet. We'll do that on Wednesday. But I wanted to go slow today so that you could see it's not that difficult and give you time to kind of think about it. The reason I want you to think about it is because this is these are values that we didn't really know how to calculate before quantum mechanics. We knew how to make tables, like for the Gibbs energy of formation and so on. We could form the molecules from their elements. But we said, by definition, we said the elements have a 0 Gibbs energy of formation. And then if we make a molecule out of those, then we're going to have some other Gibbs energy that it takes. If we make that molecule, maybe it's more spontaneous to make the molecule, and so it's a negative Gibbs energy of formation. But we just defined the elements of the elements in their standard states as having a 0 Gibbs energy of formation. Do you see how that's just totally arbitrary? We could have picked, like Gaussian picks, nuclei and electrons completely separated as their 0. And so all the enthalpy and Gibbs energy in the Gaussian calculations is incredibly negative, because as soon as you bring an electron and a proton together, it drops in energy because you're way uphill. Think about how far uphill you are. You've pulled every electron off of every atom. And so you have nuclei and free electrons. That's above every element. That's above every molecule. And so when you start forming atoms and then you start forming molecules, you're dropping downhill, downhill, downhill. And then, but you have a single reference point for every compound ever made, because every compound is made of atoms, and atoms are made of electrons and nuclei. So where the reference point is important in thermodynamics. And we just make these arbitrary decisions. That's just an arbitrary decision for Gaussian to do that. Okay. It was arbitrary for thermochemistry to say elements in their standard states is 0. But this isn't arbitrary. This is the ground state. This is the lowest quantum level in a system, and it has 0 energy. And then all the excited states from there up would have their corresponding energies, and now we can calculate the Gaussian, the Gibbs energy, the enthalpy, and so on from first principles using quantum systems. So I know y'all are new. You're just now learning this the first time, but this is revolutionary to be able to have a concrete ground state reference point and say this is truly 0 energy, and everything above it is going to give us something. So being able to calculate these thermodynamic values from a simple quantum system is a big deal. And I just showed you it's not that hard. Once Boltzmann solved his distribution problem, then that math was easily used to form all of these different systems and give us a statistical basis for thermodynamics. Okay.
Just to clarify again, what was the difference between the ones we just calculated?
I just changed this page. I just changed from wave numbers to joules per mole. Is that what you mean?
Okay.
Yeah, I was just showing you if you wanted to kind of say, well, I don't understand those wave numbers. I deal in joules or joules per mole, just to show you that these are, decent values for joules per mole. Okay, let's talk a little bit more. Oh, well, okay, that's next week, or that's Wednesday. Let's do. I'm trying to think if I have a hoot related to this first one. Let me look real quick. Or were there questions on the homework? Sometimes there's. Now's your chance.
On homework 2,
Yeah.
there was one where it was like, give the Boltzmann constant in moles for joules per mole equivalent.
Yeah.
And I know I put 8.31, and I guess I wanted 8.314. It was wrong. So I'm wondering.
Really? It shouldn't have been. Well, I mean, I think I probably, because that one's a constant, you should probably have as many digits as you can. I don't know that. I don't know how tightly I put that. I can look at it and see. Normally, if the answer other than a constant, right, which you should have as many digits, whatever. But if it's not a constant, if it's a calculation, I typically give you plus or minus 5%. So if let's say it's the answer is 6, okay, 10% of that would be 0.6, and then I cut that in half, so 0.3. So it'd be plus or minus 0.3. So in the second digit, you get plus or minus half of the first digit. That's 5%. So I think that's going to catch you for rounding differences between your work and mine. I think we'll be okay, and it has been, in for many semesters. But for something like that, I don't know. Did I put anything in the problem to indicate answer exactly or whatever. No, I can look at that. Let's see. Did anybody else miss that particular one? Huh? You got it? You did? Okay. Yeah, everybody check.
I missed it because I did it wrong.
Oh, okay.
But not because I did it right.
That's a sticker for honesty.
Unless you want to change it, I'll
That's
forget that.
That's great.
I heard that you used to give out bumper stickers if you guys keep them.
I do. Yes.
Do you still give them out?
Yeah, yeah. I was wondering if I had already given you all those. No? Okay. Okay. I'll get them. I'll bring them on Wednesday. Yeah. Have y'all seen any around town?
Yeah, Delvin has one. He has it like on
Yeah, Delvin. Yeah, that's right. That's right. That's right. That's great. I honk at them too. If I see them, I honk like crazy. People will be like, "What the heck? The light's not even green yet." I'm probably gonna cause a crash. I'd feel terrible if I did that.